All right, so in this video, we finally finished the proof of the Rogers-Ramanujan identities. But first, we'll start with a quick summary. We've taken G1 and G2 over here to be the product sides of the Rogers-Ramanujan identities, and we'd like to show that they equal the sum sides of the Rogers-Ramanujan identity. So these were our G1 and G2. Following the paper by Andrews and Baxter, we've defined Gi in the following way for I greater than or equal to 3. And the whole point of our last video was to prove what Andrews and Baxter called the empirical hypothesis, namely, we proved this claim that Gi starts as 1 plus q to the I plus the higher powers of q. So this is going to be our jumping off point, and so we can start going through the proof of the Rogers-Ramanujan identity. So let's do the following. So using our series, right, we had that G3 is equal to G1 minus G2 over Q. And what does that imply? Well, this allows us to rewrite G1. Namely, I could write G1 is equal to G2 plus Q times G3. But what else can I do? I know that G4 has this nice expression. I could write G4 as G2 minus G3 over Q squared. So this implies that G2 can be written as G3 plus Q squared G4. And we'll do the same thing for G5. We'll have that G5 is equal to G3 minus G4 over Q cubed. So this will imply that G3 can be rewritten as G4 plus Q cubed times G5. Okay, so what are we going to do with this expression? Well, we'll start with G1. I know that G1 can be written as G2 plus QG3. And what I'm going to do is I'm going to replace the G2. So I'm going to take this expression for G2 and substitute it in down here. So let's do that. So when I do that, well, G2 gets replaced by G3 plus Q squared G4 plus Q times G3. So this allows me to write G1 as 1 plus QG3 plus Q squared G4. Okay, so we have this rewriting of G1. Now, what else do I notice? Well, I have this nice expression for G3 over here. So I'm going to take this expression for G3 and substitute it down here and then continue simplifying. So let's do that. So when I do that, what do I get? I'm going to get 1 plus Q. G3 gets replaced by G4 plus Q cubed G5 plus Q squared G4. Right, and I could simplify this a little bit more. When I rewrite this, what do I get? I get 1 plus Q squared times G4 plus Q cubed plus Q to the 4th times G5. Okay, so now we have G1. We first wrote it in terms of G2 and G3. Then we were able to write G1 in terms of G3 and G4. And then we were able to write G1 in terms of G4 and G5. And you could imagine that we can continue this way, right? So using our recursion, we can continue this way. So what we could say is continuing this way, I can write that G1 can be expressed as AI times GI plus BI times GI plus 1 for I greater than or equal to 2, where the AI and BI are just polynomials in Q. These are polynomials in Q. So notice from our above expressions, one thing to notice is we've already found the first few A's, right? So we had that A2 was equal to 1. That was our coefficient of G2 in our very first expression, right? So our A2 is the coefficient of G2 up here. A3 is equal to 1 plus Q. So A3 is just our coefficient of G3 when we did our first rewrite. So A3 is 1 plus Q. A4 is 1 plus Q squared, right? And that's just our coefficient of G4 when we did our rewrite, right? And of course, we can also figure out what the B's are, right? So B2 was Q, B3 was Q squared, and B4 was Q cubed plus Q to the 4th, right? So we're going to focus primarily on the A's. The B's are not going to be as important for us. So the first thing we're going to do is to try to derive some relationship between our A's, try to derive some sort of recursion that the A's might satisfy. So the first thing to recall when we want to do this is that we have this nice definition of the g's. We can write gi plus 2 is equal to gi minus gi plus 1 over q to the I, right? And so if I rewrite this expression, I'm using the fact that gi can be written as gi plus 1 plus q to the I times gi plus 2. Okay, so we're going to use this to derive some sort of recursion satisfied by the polynomials, the a's and the b's. Okay, so how do we do this? Well, let's start. We're going to have g1. We're going to assume it can be written in the form aig1 plus bi, or aigi plus bi times gi plus 1, right? And where do we go from here? Well, I know that gi can be replaced by this expression above. So I'm going to take this gi and plug it in here. Right? I know I can do this replacement, so there's going to be ai times gi plus 1 plus q to the I times gi plus 2 plus bi times gi plus 1. Okay, so let's combine our terms. Let's put some stuff together. This is going to be, well, what are the gi plus 1 terms? It's ai plus bi times gi plus 1. And what are the gi plus 2 terms? Well, there's going to be a q to the I ai times g sub I plus 2. All right, so we have an expression that looks like this. And the thing to notice over here is that all we're looking at here, this is our ai plus 1. And this guy right here is our bi plus 1. Right? So remember, the idea is that the ai's go in front of the gi's, the bi's go in front of the gi plus 1s. Right? So this is our new expression. And so we're able to write something quite nice down, right? We're able to say a sub I plus 1 has to equal a sub I plus b sub I, and b sub I plus 1 has to equal q to the I a sub I. So now we can put these two expressions together, and we get this rather nice recursion for the a sub i's. Namely, we get that a sub I plus 1 is equal to a sub I, and now if I replace b sub I with the expression beneath our expression for the a, I'm going to get q to the I minus 1, a sub I minus 1. Right? And this holds for I greater than or equal to 3. Okay, so these are our expressions. So let's see what the first few of these look like. We've already written these down, but I'm going to write down the first few expressions that we can get this way. So we saw earlier that a2 was equal to 1, that a3 was equal to 1 plus q, and a4 was 1 plus q squared. Right? And then using our recursions further, we can derive, well, any of the a's that we want, right? So using the recursion above, I can say a5 is 1 plus q squared plus q cubed plus q to the 4th, but I'm deliberately going to write this as plus q to the 3 plus 1. Right, so this is our a5. I can do something similar for a6, right? I write a6 as 1 plus q squared plus q cubed. And now we're going to get 2 q to the 4ths. So I'll write one of them as q to the 3 plus 1, and the other one as q to the 4. And then we're going to have a q to the 5th. So I'll write this as q to the 4 plus 1, and a q to the 6. So I'll write this as q to the 4 plus 2. And I'm doing this deliberately because I'm trying to capture different partitions in the exponents, right? So the thing to start noticing is that the partitions that appear up here as our exponents, they all satisfy the difference 2 condition, and the parts are kind of limited by whatever our subscript is. So if I have an a sub 6, the largest part I'm allowed to use is 4. Right? So we might be able to make a conjecture based on this, right? So we might notice, that a sub I plus 1, it captures partitions with largest part, or into parts that are less than or equal to I minus 1, right? So a sub 6, the largest I'm allowed to use is a part of 4, with difference 2, with difference which is greater than or equal to 2 between the parts. Right, so we have these nice polynomials, and we can see if we further write these out that this pattern is going to continue, right? So we've basically confirmed this for everything up to, well, we've confirmed this for I equal to 1, 2, 3, 4, and 5, right? So this is I equal to 1, I equal to 2, I equal to 3, I equal to 4, I equal to 5. Okay, so we have some confirmation of this. We have enough evidence. So based on our evidence, we can now make the following conjecture, the following claim. We'll show that ai plus 1 is the generating function for partitions of n into parts that are at most I minus 1, and which have difference greater than or equal to 2 between parts. So we'll prove this by induction on the subscript. So the first thing I'm going to point out is that the base case is clear, right? We saw this in our examples above. So this is clear from earlier. So what I'm going to now do is I'm going to suppose that the claim holds for a sub k, where k is equal to 2, 3, 4, up to I. Right? So I'm going to assume that a sub k is the generating function for partitions of n into parts less than or equal to k minus 2, which have difference greater than or equal to 2 between parts. Okay, so we've taken a second to write that down. So the assumption I'm making is the assumption in orange. So now what I'd like to do is I'd like to take a partition of n into parts that are smaller than or equal to I minus 1 with difference greater than or equal to 2 between the parts. Right? So also, so notice that any partition of n into parts that are less than or equal to I minus 1 with difference greater than or equal to 2 between parts, it satisfies one of two conditions. So this satisfies, well, one thing I can do is I can say, okay, if my largest part is actually I minus 1, and I remove that part, what I end up getting is something whose largest part is at most I minus 3 because of the difference 2 condition. So if my largest part is I minus 1, I remove that part. The largest part now is allowed to be I minus 3 or smaller, right? So in this instance, so this partition has largest part I minus 1, and removing this part leaves behind, so removing this part leaves a partition behind which is counted by ai minus 1. Right? ai minus 1 has largest part I minus 3 and has the difference 2 condition. Right? So if I have something with difference 2 condition, has largest part I minus 1, and I remove that I minus 1, I still preserve the difference 2 condition, but now my largest part is allowed to be I minus 3. And so we know that this is going to be counted by a sub I minus 1. And the other condition is that I don't actually have any I minus 1s. And my largest part is less than or equal to, so this has largest part less than or equal to I minus 2. And in this case, this is counted by a sub I minus 2. Right? Or rather, sorry, a sub I. This is counted by a sub I. Okay, so any such partition, so thus, any such partition is counted by, well, q to the I minus 1 times a sub I minus 1, where I'm using the q to the I minus 1 to represent the largest part I minus 1 that I've pulled out. So partitions here, or a partition already counted by a sub I. The thing that I notice is that these partitions, they satisfy the exact same recursion as the polynomials. So this is just a sub I plus 1. Right? So they have the same initial conditions, they satisfy the same recursion, therefore they must be the same object. So I could say, hence, our claim is true for k equal to I plus 1. And thus we've proved our claim by induction. So we've proved this statement, and now we're finally ready to complete our proof of the Rogers-Ramanujan identities. So one thing to recall from earlier in the video was that we were able to take G1, and we were able to write it as AIGI plus, well, we wrote BI times GI plus 1, but we showed that BI can actually be rewritten as Q to the I minus 1, A sub I minus 1, G sub I plus 1. Okay, so what is the trick we're going to use? We're going to now take the limit as I goes to infinity, right? How do I take the limit of a series? Well, I'm going to just ask, as I gets larger and larger, what do the coefficients stabilize to? So for example, I'm going to take the limit as I goes to infinity of G sub I. Well, what am I doing? I'm basically taking the limit as I goes to infinity of 1 plus Q to the I plus higher power terms. And the thing that I notice is, what do the coefficients eventually stabilize to? Well, as I gets larger and larger, all the coefficients after 1 become 0, so the limit of G sub I as I goes to infinity is just going to be 1. All right, so we're going to use this fact. Okay, so what am I going to do? I'm going to say, okay, G sub 1 is going to equal the limit as I goes to infinity of AIGI plus Q to the I minus 1, AI minus 1, GI plus 1. All right, so it's the limit of this expression. And what does this leave me with? Well, I can rewrite this as the limit. I'll leave this as something to check. The limit of AI times the limit of GI as I goes to infinity plus the limit of Q to the I minus 1, AI minus 1 as I goes to infinity times the limit of GI plus 1 as I goes to infinity. All right, so we could rewrite this way. What does this leave me with? Well, this leaves me with an expression I'll call A sub infinity times 1 plus, the thing to notice is this term, as I goes to infinity, all the coefficients here stabilize to 0. So what I'm going to get is 0 times 1. And so I'm going to be left with this expression A sub infinity. And what is A sub infinity? Well, A sub infinity, this is just the generating function of partitions of n with difference 2 between the parts, so with difference greater than or equal to 2 between parts. And now I no longer have a restriction on the size of the parts. So with no restriction on the size of the parts. So what is this? This is just the other side of the Rogers-Ramanujan identity, right? So this is what we call the sum side. So we get that A sub infinity. What is this? This is just going to be the sum of Q to the n squared over Q sub n as n goes from 0 to infinity. So we've proved the first Rogers-Ramanujan identity, right? We showed that this was equal to G1, and remember, G1 was our product side. So G1, just to recall really quickly, was 1 over 1 minus Q to the 5n plus 1, 1 minus Q to the 5n plus 4, as n goes from 0 to infinity. Right, so we've proved the first Rogers-Ramanujan identity. As an exercise, I'll leave the proof of the second Rogers-Ramanujan identity. So exercise, repeat this, starting with G2. So starting with G2 instead of G1 to prove the second Rogers-Ramanujan identity. So it's the same exact proof, we just have different initial conditions for our polynomials to prove the second Rogers-Ramanujan identity. Okay, so we finished our proof. This is the end of the motivated proof of the Rogers-Ramanujan identities. So there's one loose end we've left unattended, which we'll answer now. So our original motivation, the reason this was named the motivated proof, was to answer Aaron Price's question. So starting from the product sides of the Rogers-Ramanujan identities, can I show that G1 minus G2 has non-negative integer coefficients, right? And which is, we showed equivalent was equivalent to showing that G3 has non-negative integer coefficients. So the answer is yes, and we actually repeat the same process that we used earlier, right? So one thing I know is that, well, G3 can be rewritten as G4 plus Q cubed G5. And what do we know? Well, I know that G4 can be rewritten, so I know that G6, for example, is defined to be G4 minus G5 over Q to the 4. So this tells me right away that G4 can be rewritten as G5 plus Q to the 4th G6. So we can replace this G4, so I can take this expression for G4 and substitute it over here. So let's do that. I'll get G5 plus Q to the 4 G6 plus Q cubed G5. But if I collect my terms, what do I end up with? I end up with 1 plus Q cubed times G5 plus Q to the 4 G6, right? So just like earlier, I can continue in this way. And what I'm able to do is I'm able to say G3 can be rewritten in terms of some polynomial AI times, let's call it AI prime to differentiate from the polynomials earlier, times GI, plus Q to the I minus 1, A sub I minus 1 prime, G sub I plus 1, for I greater than or equal to 5. And I can show that these polynomials satisfy the same recursion as earlier. They just have a different initial condition, right? We have to take the initial condition that A4 is equal to 1 and A5 is equal to 1 plus Q cubed when we set up these polynomials. So as before, it's clear that if I keep building up these polynomials, so from the recursion, it's clear that AI will always have non-negative integer coefficients. Why? Well, all I'm doing is I'm taking positive multiples of Q and positive multiples of my polynomials, which already have positive multiples of Q, or rather non-negative multiples of Q. So AI will have non-negative coefficients. And taking I to infinity, so taking I to infinity finishes the proof of the claim. So finishes the proof of the answer in the affirmative to Aaron Price's question. Okay, so I'll stop here.